Hello, everyone. Thank you for joining us today. We're going to wait for a couple more minutes to make sure that everyone who's planning to join has time to join us, and then we'll get started. If you can't hear me or see the presentation, go ahead and post something in the chat window, but otherwise we're just going to stay on hold for a little bit longer. And hello again. This is Leah Freeberg from Fluke Excelix. Thank you so much for joining us today. Looks like people are still logging in, but I'm going to give you a little bit of background or information here. In particular, you probably all know Fluke as a test tool provider, but for the last 10 years or so, our passion has increasingly been around making the measurement data that our tools collect more usable for reliability maintenance. So the company of today, Fluke of today, produces software and sensors and cloud platforms and a lot of other reliability and inspection tools. We were actually just talking with Doug about what the reliability engineer needs today and how whether that's any different from 10 years ago. So you'll find that our best practice webinar series focuses not just on technology, but on the maintenance strategies and solutions. And for that reason, it features speakers from a variety of expert backgrounds, like Doug. So we're really, really pleased to have Doug join our program today. Many of you know him. He's a noted maintenance and reliability expert and the founder of RCM Blitz. And he'll be presenting on how to focus your efforts on asset lifecycle to improve reliability. So Doug, if you want to advance to the next slide, we'll take a look at your bio here. So you know Doug as a longtime maintenance and reliability expert, founder of RCM Blitz, and he's provided reliability training and services to numerous companies around the world, large and small, including Fortune 500 companies like Cargill and Kraft, Cooper Tire, DC Water, Whirlpool, Honda, Coors Brewing, Energizer, Corning, Invista, Newmont Mining. But here's where it gets interesting. Doug has also made key contributions to standard reliability measures for manufacturing reliability training programs for engineers and managers, technicians, and skilled trades. And he's trained so many client RCM facilitators and performed RCM analysis on hundreds of pieces of manufacturing equipment. Prior to all this, Doug worked for 19 years at Eastman Kodak in Rochester, New York. And he's had positions from skilled trade person up to maintenance supervisor and reliability engineer. And he holds a certificate in reliability engineering maintenance from the one and only RIT. Good morning, Doug. Thanks for joining us today.
Good morning.
Excellent. So before you get started, I wanted to ask you something. So I see the PF curve presented in a lot of different ways out there. And I'm curious about what influences your particular approach to the curve.
My particular approach to the curve is the curve that most people look at is only just a portion of what goes on in the life cycle of an asset. And that's by the time we get to point P, it's often too late. If failure has already occurred, point P is the point where we've actually just first detected it. So I want people to go back and focus on what caused that failure to begin with. Was it something in design? Was it something in the installation? Was it something in terms of how we operate it? There are many things that could cause a potential failure. So that's really been my passion, is to get people to focus on the entire asset life cycle.
Thank you so much, Doug. I can see in the question bar we already have some curves about, or some questions about what is the PR curve, so this is going to be perfect. I need to tell everyone that today's session is being recorded, so your phone lines are muted so we can minimize background noise. And then we're going to save time after the presentation for questions. So you'll see the question feature over on your toolbar there, and you can submit questions anytime, and we'll be reading them. But we're going to wait until the very end, and then I'll read them out loud, and Doug can take his time responding to everything. If you'd like to receive Doug's slides from the presentation, we'll put a survey up at the end, and you can click there to say that you'd like the slides, and then we'll send them over to you. And the recorded webinar will also be available afterward on excelix.com under our community part. So that's it. Doug, it is over to you.
Thank you. All right, so starting out with the basics of the PF curve, this is something that my first exposure to it was reading Stan Nowlan and Howard Heap's paper on reliability-centered maintenance, and their discussion of the PF curve and actually their illustration of it, which amazingly enough didn't include points P and point F. Right now, they labeled them as potential failure at point C here and functional failure at point D. Right, and later on, illustrations that they made in different work they did called this the PF curve. And notice that point P is further down this curve than what we typically see it, right? That's a potential failure. And that's one of the things that a lot of people aren't aware of is that points P and point F both move or can move up and down on that curve depending on how you're or what tools you might be using to detect potential failures or detect failure conditions, and what you determine is functional failure can move point F further up that curve. So point P again is for potential failure. It's the identifiable physical condition that indicates functional failure is imminent. And these are Stan Nowlan and Howard Heap's words, by the way, which I always tend to fall back to because there is so much information that's put out there about the PF curve, and a large percentage of it is incorrect, right? I'm always going to go back to the people that developed this particular part of reliability engineering. Point F, again, is functional failure. That's the inability of an item to meet specified performance standards. So the PF interval is the time it takes to get from point P to point F. So some of the problems with the Nowlan and Heap PF curve, while point P has become the focus of companies who want to improve asset reliability, the problem is point P is too late. The failure mode that caused point P has already occurred. So while it is nice to say, gee, we're using vibration analysis, we detected an increase in vibration, we detected point P, the first question you should be asking yourself is, why did point P occur? What caused it? Point F is functional failure. Again, large percentage of those in the industry believe point F is actually represented total failure, and that's not true. It's functional failure. Your equipment is still running. It cannot perform the desired function you purchased it or expect it to do. So in terms of PF interval, think conceptual when it comes to the PF interval. Lots of people always say, well, so how do we know what our PF interval is? Well, realistically, you'd have to make sure all conditions are identical and then run the item to failure several times to determine what your PF interval is. So in most cases today, when we talk about the PF interval and how often we should do a non-condition task, it's done by industry standards, which were developed through reliability statistics. Adding to the confusion, there's dozens of different PF curves. If you look it up in Google or Bing, you'll find all these different images. Many of them were well intended, but some of them realistically aren't even close to what Nowlan and Heap described as the PF curve and the importance of it and what we use it for. So be careful what you're looking at that's out there. And again, even copying and using in presentations, because I've seen some presentations in the last year with representations of the PF curve that are not accurate. This is one as an example, right? So notice where they're showing point P, and that's where they're saying this is where we should be doing condition-based maintenance. Well, that's not true. You should be doing condition-based maintenance right from the time you install an asset or a component, right? And the time-based maintenance comes before that. Well, there are different failure modes that trigger time-based maintenance versus condition-based maintenance. So, and I'm still not sure where the warranty coverage plays into this. So really, again, it was a very confusing PF curve in my view. So going back to the basics, the curve was developed to help drive good maintenance practices, right? Again, think concept with this. You either have a useful PF curve or one that's not useful. And that's the difference. Is one of the things that people don't understand is every component at your site fits the PF curve in terms of a model. The difference between one component and the next is the PF interval, useful or not useful? For bearings, for example, we can have months in terms of a PF interval. For a proc switch or an IO card, it's going to be portions of a second. That's not a useful PF interval. So you can't do any type of maintenance to mitigate that particular failure. So, but again, understand that point P is not where failure occurs, and point F is not totally failed, but instead it's functionally failed.
All right, I'm going to take a little bit of a break here. And in a minute, I'm going to pop a poll up on screen that you guys can all select your answers to. I'm going to read it out loud first. The question is, what maintenance strategies are you currently employing? Are you mostly, and this is obviously no one's in 100% of anything, but where is the majority? Reactive, preventive, predictive, or prescriptive? Do you see the poll up on your screen now? I'll give you a minute and click the one that is closest to where your team spends the majority of its time. And when I think that we're just about there, I'm going to close the poll and then we'll get to see the results. Getting closer. All righty. I'm going to close her down. And we have got, under reactive, 48%. Under preventive, we've got 65%. Under predictive, we've got 23%. And under prescriptive, we've got 6%. Alrighty. I'm going to hide this poll and give it back over to Doug.
Okay, so moving forward, why is the PF curve important? Well, number one, it helps illustrate to people to improve fundamental understanding of how maintenance should be performed. It tells us that, hey, we have certain types of components that fit this PF curve and failure modes that fit this PF curve. And the illustration helps people understand why on-condition maintenance or predictive maintenance is important. So it makes clear how we decide whether we should maintain something or run it to failure. And it makes clear the business case for on-condition maintenance, which is also known, and it's one of the things I wish I could change in our industry, is we call on-condition maintenance several things: predictive maintenance, condition-based maintenance, condition monitoring. They're all pretty much the same thing. So understand that. As companies look to introduce on-condition maintenance tasks, they're almost always introduced to the PF curve, which helps illustrate the benefits of detecting these potential failures in an effort to improve reliability and reduce costs through planning and scheduling. So while the PF curve does an effective job of making this point, it only illustrates a portion of what an organization can do to achieve and sustain reliability throughout the life cycle of your equipment. And the reason I talk about this is for years there were many, many presentations that said focus on point P, focus your maintenance strategy on point P. And I kept looking at people and saying point P is too late. Point P is the failure has already occurred. Now we've just detected it. So what can we do to actually eliminate failures or prevent failures to begin with, along with display the importance of having a good condition monitoring program or on-condition maintenance program. So, and from that came this, what I call the asset reliability curve, or the asset life cycle curve, which starts with design. So you can see it still has the same X and Y axis that Nowlan and Heap had in terms of resistance to failure and time. It just shows a longer period of time. And again, this is conceptual. It starts with design, looks at the proactive domain, installation, the point P or potential failures, that corrective domain, and then the reactive domain. So the visual look at the different phases of this asset, from the time it's designed to the time it fails to perform its intended function. So that's why I put it there, is to say, let's look at the entire asset life cycle and then think about how you should perform maintenance. So the intent of this DIPF interval is to illustrate where reliability tools and techniques are needed to be applied to have the most impact of reliability. So point P is design. That's where the team is selected to procure capital and design the asset to a desired level of reliability. And in my illustration, you see that line go up and it levels off to say this is where it should be. I always tell people, geez, if I'm the person that's charged with designing this, I actually want to design that capability above where we expect to run. Because I know that at some point in time, as soon as we meet expectations, somebody's going to say, let's increase those expectations. So point I is where equipment is installed and put into service. Point P, once again, is potential failure, and point F is functional failure. So again, there's looking at this, and what I was discussing was saying, geez, if I'm charged with this design, I want to design it up maybe to this level of expectation, knowing that at some point in time, if we run really well at this level, some manager is going to say, let's increase the expectation or output of this system. So if a design above that, then we've thought in advance to say that's going to change. So looking at each of these domains, and point D is where the inherent design reliability of your system is determined, and that's important to understand. If we need a reliable asset, that begins with design. So we design to achieve or exceed specific performance standards, and it's important to understand that once your asset has been installed, all the maintenance in the world won't improve the reliability of a bad design. So if we do a great job in design, all right, we still have some things that need to be met to get that equipment to run at what we designed it to do, and I'll talk about those coming up. So tools for improving reliability in the design phase. We have FMEA. Most people are familiar with failure modes and effects analysis. We can do RCM. We can look at developing design standards in terms of, let's look at our rotating assets, for example, and say how much, in terms of rotating assets, how much foundation in terms of mass needs to be poured to support a good rotating asset. Requirements documents. So if I buy a brand new gearbox from a company and we have this design that's put together, I want them to sign off that when it's installed, this is the level of vibration we expect it to run at, this is the temperature it should be running at, and so on. Select supplier agreements. This is one of those that lots of companies, they lose sight of this in their purchasing organizations. We say, okay, rather than go out and bid every single type of component on this project to 3 or 4 different companies, and doing that in the past, that's how we've ended up with 10 and 12 different brands of motors in our stock rooms, and 15 different brands of centrifugal pumps, and 9 different brands of starters, and 8 brands of VFDs, and so on. Start looking at the components that actually are giving you good reliability, and look to make select supplier agreements with the manufacturers of those components. Again, we can do reliability block diagrams at the beginning of the design phase to determine what level of reliability we should be able to achieve. And of course, putting in place during the design phase. This is extremely important, and it often gets put off until afterwards. Maintenance and reliability foundational elements. So we need to have that equipment hierarchy built, criticality analysis performed, and a bill of materials. And from that, we can do those other tools like RCM and develop a good maintenance strategy so that when this equipment hits the ground running, we have a maintenance strategy in place that's going to ensure that IP interval, so the time from the time of installation to the time of the first potential failure. And that's where the money truly is in terms of saving cost and manufacturing more, right? That's that proactive domain I talk about here in the yellow. So moving on to that proactive domain, point I is installation, and this is where the reliability of your design is either ensured or destroyed. And this is one of those, I see this over and over again with my customers. They'll go out and they'll put together a good design, and then they'll bid out the installation to a contractor, and they have no idea who's coming in to install this equipment, whether they understand precision maintenance techniques. So can they do laser alignment or reverse dial indication alignment? Do they understand proper support? You name it, anything that, when it comes to installing, we can either do the job right or do the job wrong. And if we do the job wrong, you are going to live with that for the remainder of that asset life cycle. So your IP interval is going to be drastically shortened if it's not done right to begin with. So the proactive domain includes PM, on condition task, and failure finding task. It's in this domain where we recognize the return on investment for the precision work we did at the time of installation and for completing our proactive maintenance task as scheduled. Focus on point I and the IP interval. That's where the most important phase of the asset life cycle is, doing things right in this particular phase of the game. So we have another poll.
We do. And crazily enough, it's right on topic for what you were just discussing. So this time I want to clarify that you can choose as many of these as apply to you. So the question being, what tools do you currently use to improve maintenance practices? I'm going to turn the poll on, and you can choose as many as are relevant to you.
Do you have that Jeopardy music to play?
I think people are thinking about this one.
Doug, could you go through the definitions for the 4 items, or at least the 3 acronyms?
Yes, FMEA is failure modes and effects analysis. That's a tool typically used in the design phase of equipment. RCM is reliability centered maintenance. That's a tool we can use in the design phase or at any time in the asset life cycle to develop a maintenance strategy. Root cause analysis is for getting together and discussing and determining the causes of different failures that have occurred at your site. And TPM is total productive maintenance. It's a tool that was developed to help operations work with maintenance to improve reliability and equipment performance.
Okay. I am going to close the poll, and I'm going to share it. And now we can see that people, about 30% of us feel like we're doing FMEA, and about 29% of us are in RCM camp. 75% are in root cause analysis, and 30% are in TPM. Well done, everyone. And back to you, Doug.
Okay, so tools for improving that IP interval. So these are things that we can do around improving our installation practices. So we can do RCM. It can be done anytime. It can be done during the design phase or afterwards. Precision alignment and balancing. Having torque specifications and using torque wrenches to install pipes, looking glasses, you name it, even electrical panels, torque for those. installation standards and job plans. So installation standards gets into, all right, if we install a pump in terms of suction and discharge, how much straight pipe should be there before we have any restriction in terms of valves or fittings? Where should the first hangers be located? How far should our hangers be apart? Those types of things. Use the use of predictive tools at commissioning, vibration analysis, for example. Before we turn the equipment over to operations, we should be getting a baseline vibration to make sure that the equipment has been properly aligned and balanced. Use of precision tools, and this is one that sometimes confuses people because I ask them what are precision tools, and they start talking about verniers and calipers and torque wrenches and you name it, and those things all are precision tools, but I tell people precision tools sometimes are just the right tool for the job. Let's not use a pipe wrench where I should be using an 1.25 inch ratchet and socket and an 1 1/8 inch combination wrench to take a 3/4 inch bolt apart. Right? If we use the right tools, then the next person can do the job effectively when it comes to disassembling and reassembling. If we don't use the right tools, you mess up the nut and the bolt and you can't get the proper tools on. So QA and QC inspections at installation, this is really, if I look at this list, probably one of the most important things and things that we continuously fall down on. If we have a new project and we've got some contractors out there doing an installation, you should have a couple of your maintenance people, electrical, instrument, mechanical, going behind these people and making sure they're doing an adequate job of installing these assets for us, that the work that's being done is quality work so that we get that nice long IP interval I talked about. So looking at the proactive domain, our maintenance strategy is on condition maintenance, failure finding, tasks, and PM. These things should be identified and performed at their specified intervals, and we should not sacrifice on those. That's one of the things I'm talking about and trying to get the point across in terms of the industrial Internet of Things and smart machines and reliability centered machine learning, all these new articles and things that are coming out. It still comes down to we have to have managers that are smart enough to say that the intervals that we recommend we do these things are important and we cannot sacrifice those. That's what makes this work. All our tasks that we decide on should meet the criteria for applicable and effective that comes out of RCM. Don't let those schedules slide and understand the importance of criticality in planning and scheduling maintenance. So moving on into these corrective domain, and again, this is also known as the PF interval. There's tools and strategies we can do there. Root cause analysis. Again, once we identify point P, the first question that should be asked is, what caused it? That's a great thing for root cause analysis. What caused your point P to come in? Plan and schedule that corrective maintenance as soon as point P is detected. Right? We can use our PDM tools to monitor fault progression. I can tell you, I am not big on that. I've seen companies do it, and some companies that do it reasonably well. And what I mean by that is they're not doing it to enhance their run to failure strategy. And what I mean by that is, well, they'll start doing more condition monitoring to say, how much more life can I get out of it? The reason we do condition monitoring is to detect point P, plan, schedule, and replace before we have secondary damage, right? If you continue to just monitor things, the secondary damage is starting to go on, right? So what's the point of doing this if you're just going to continue to delay while you're damaging the equipment? The downtime is going to do nothing but increase, and the cost is going to increase. So let's get disciplined and say, when we detect point P, we're going to plan, schedule, and at first opportunity, replace that item. Right. On top of that, we have our consequence reduction techniques and strategies we can use in terms of stocking of spares and so on. All right. In terms of the corrective domain, understand that collateral damage. Efforts in this domain should drive two behaviors: determine the cause of the failure and look to mitigate or eliminate and then address the failure and minimize the collateral damage or the secondary damage. Moving on into the reactive domain, and that's where lots of us live. You don't have many choices here. You can either shut the equipment down or run it to failure. In either way, you're going to open your checkbook. Lastly, you're going to cross your fingers and you hope that it doesn't happen again. Realistically, we need to learn from our mistakes. Let's use the tools available, the RCM, the root cause analysis, the FMEA to discuss and determine why we have the failure modes that we see, right? And what can we do to mitigate those things? So if we focus our efforts here on this last portion of this curve, of this asset lifecycle curve, your maintenance costs are going to continue to rise. Your assets won't be reliable, so you're going to miss making orders, right? You're not going to have the ability to plan to manufacture and deliver, and customer orders are going to be impacted. So we all have a choice, and I tell people you can live out here at the end, and most companies that I work with do. And it's the most expensive place to manufacture and to perform maintenance. Or we can do the task up front. And I have a few of those customers that have learned that. I'm working with one right now, and I'm just delighted with the fact that here they are at a point where they're just beginning to start their equipment to make this particular product that they designed this equipment for, and we're building a maintenance strategy. They've done their foundational elements. They have the hierarchy in place. They've done a criticality analysis, and now we're putting in place a maintenance strategy that's going to go long, and it meets all those things, so that when it comes time to making product and planning to meet deliveries, they also recognize the fact that they need to plan to do their PMs and their on-condition maintenance. So I have a high expectation of what's going to come out from this project. All right. So at this point, that completes the presentation. We can do a question and answer period.
We certainly can. Thank you so much, Doug. We're going to start with the questions that have already been entered, and then as you guys have more questions, please just keep popping them into the tool, and we'll get through them. So Alan Wood asked a question back about QA and QC, Doug, and he started by asking, how does Doug recommend that we ensure that we have qualified inspectors? And then he says the question is relevant because they had a new facility, and they discovered a section of pipe that was insulated but wasn't coated, and that led them to question the quality of their QA and their QC. So it goes back to, how do we ensure that we have qualified inspectors?
All right, your qualified inspectors should come right from your own skilled tradespeople. That's my hope anyway. Right? And by interviewing those folks, you should be able to select people that you'd want to work on different projects. Now, with the understanding that may change depending on your plant size and the type of equipment you're installing, because some tradespeople will be experts on some types of equipment, and you might have others that have more experience on different types. So to me, it would be interview your tradespeople and let them select the people.
All right. And if that doesn't cover the full answer, just let me know in here. I'm going to back up a little bit. Tony asked whether Fluke has the ability to participate in IoT as a collection and a transmitter. And I don't think that's going to be Doug's territory to answer. I can clarify a little bit, and then Doug can tell me if he thinks I'm wording it appropriately. But so Fluke does have cloud-based data tools. In other words, many of their tools will collect reliability data, both streaming and handheld. And you can upload that data, you can then track it in management, you can set alarms and so forth. It is not fully predictive at this point, but yes, they do collect and transmit and manage data using the IoT. Then going on down, some folks had questions about reliability block diagrams, but I think you went over that. I think you went over that pretty well. I think we're good there. Question for you, Doug. Whether you help manufacturers implement CMMS systems, including Fluke's eMaint software.
I have seen Fluke's eMaint software. I have given advice to companies on that in terms of how they should build that, what their hierarchy should look like, what a good criticality analysis looks like. So in terms of, I give advice and consult on that. In terms of, do I help them install it? No.
Right. Any good CMMS provider should be out there helping a new site come on board. It should be part of the package. And then someone like yourself is highly valuable for determining asset priority and the rest of the fundamentals that that go hand in hand with it, right?
Yep.
Yep. All right. Going down to the next question from Karen. She asks for contractual language to specify the design and commissioning for CIP and high dollar replacements.
Yeah, that's that's where your corporate attorneys come in.
Yeah.
I can tell you, I'm not that. I looked at several of those types of things, and I know way back in my Kodak day, we did have requirements documents for vibration, temperature, noise on all of our rotating assets. And I know our corporate attorneys helped in terms of those contracts to make those clear. All right, I can tell you, and I won't mention the name of a company, but one company that made mixers just had fits because it came down to that they couldn't pass, and we said, it's on your back, right? You either fix them and make them right, or we'll pull them out and we'll go with somebody else, right? And it took them a few months, but they finally did come up with the solution to meet the criteria that we put in. And as a result, those things ran for years and years and years and years and years before we saw point B, right?
I think that was a pretty good answer, and you're not a liar. I mean, as far as I know. So well done. Karen also asks if you have a list of items for baseline testing when you're commissioning a new motor.
Do I know what the baseline should be? No, I don't. Do I know people that could probably give you that information? Yes, I do.
I think it sounds more like a checklist. Like, is there a standard procedure?
Yeah, you know, in terms of standard procedures on a motor, you're going to want vibration analysis. You're going to want to do MCA on that motor, right? And get a baseline temperature on it when it starts up and has been running for, say, an hour, right?
Yep. All right, here's a good one, Doug. The listener asks, I believe that machine learning and artificial intelligence will change everything we know about RCM as it becomes more accurate and efficient. What is your view on that?
I think it will help in terms of general or what I call engineered failure modes. I think it's going to struggle just like other tools that we have, because this is a discussion we were actually having before the presentation started. Is there's nothing really new in terms of industrial Internet of Things and smart machines. We just have faster computers that are capable of crunching more data. The instruments that we have today in terms of wireless and online vibration analysis and IR and ultrasound and pressure, temperature, flow, timing, all those things have been available for years and years and years. What we have now is just the ability to do more number crunching, right? So while I could have a smart machine that says, okay, I've got all these electronic parts as well, and so I'm going to start creating based on reliability statistics, intervals of when you should change an I/O card. Right? I'm going to turn around and say to you, how do you know why the I/O card failed? Right? And if I change it today, was it improperly installed, or was it a temperature issue? Until that smart machine learns those things,
right?
We're still going to have some foggy areas and a lot more information to digest. So who's going to digest that information that gets spit out? All right. In the same sense, while we have all these tools, vibration analysis, thermography, and you name it online, they're no different than we've had in the past, where somebody's still going to have to tell the smart machine it's time to shut down.
Mm-hmm.
So is the machine going to do it itself, or is it still going to be a manager that says, I need to make product?
Yep.
Right.
So no replacing experience and an engineer.
Right.
Mm-hmm.
So nothing replaces that. Will it change RCM? I think it will a little bit. I think there'll be more people that want to lean towards failure mode libraries, and I've done articles on why some of those things work and why some of them don't.
Mm-hmm.
You know, a new process of failure mode library is not a bad place to begin. Right, a process that's 5 or 10 years old, where you've got experience, you go, you're going to find the things that are really causing you your problems weren't in that failure mode library. They're how we operate, the environment that we live in.
Yes.
Right?
Yes.
And do work in. The experience of our people has a huge impact on that. What are those failure modes?
Yep.
Does a smart machine tell me how experienced my people are?
Mm-hmm. Mm-hmm.
Not that I'm aware of. So are those things good? Yes, they are. I'm excited to see what that brings, right? Realistically, not much has changed other than the fact that we've got more data to process.
Thank you.
You're welcome.
So I have a further question from Karen. She is the one who asked about the baseline testing standard practices for commissioning a new motor. And then she asks further for enhanced pump and motor add-ons for wastewater.
In terms of that becomes a little industry specific, right? What are your flow rates coming in? What are your flow rates going out? What's the differential pressure across there? So where do you sit in that pump curve for that particular pump?
Mm-hmm. Okay.
So again, I'm going to recommend in that you would have some type of vibration analysis on the startup, and then again, where based on the calculations you did beforehand, right? Is that pump operating in the curve where we expected it to, based on what was the expected flow, what's the expected output?
Okay. And the fellow who had the QA question came back and said, yep, we used a third party, apparently the wrong third party. And then he asked a different question. He said that you spoke, Doug, about a baseline on installation, baseline vibration data. If we did not do that, he asks, I assume it is okay to begin a baseline after the equipment has been in service?
Well, you're going to get some kind of reading, but it's certainly not going to be your baseline, right? I mean, if you're lucky, it's going to be close. It's going to show you there's no misalignment, there's no imbalance, and they did a good job of installing it. If they didn't, you aren't going to know what your baseline truly is.
But you may still get started, right? Like if you didn't, there's no.
Yeah, you've got to start sometime.
Yeah.
So should you start? Yes, you should.
Okay. All right. Dave asks, do you have any tips to get buy-in from plant leadership who may think that reactive maintenance is the norm in industry? I knew you'd chuckle.
I don't mean to laugh, but I've been there so many times, and this is where, in the courses that I teach, I try to tell maintenance people, we need to become business people. We need to talk about the money. Money is where this is at, right? What's reactive maintenance costing us? And use real numbers, right? Because there's a lot of fudge numbers out there that say, oh, reactive maintenance is 3 to 5 times more expensive than doing on-condition maintenance and planning and scheduling, right? The numbers I see are actually higher than that, right? So use actual numbers. Say, all right, here's a pump where we actually did that. We said we're going to do vibration analysis on it. We're going to detect when it's about to fail, and we're going to, or it's in the progression of failure. We're going to go out, we're going to pull it, we're going to rebuild it, and this is what the rebuild cost. And here's one where we said, oh, we don't have time to do that. We don't have time. We need to do this. We need to pump. We need to go. What's the cost of repairing that pump? Or were you actually able to repair it? Did you have to buy a new one? Right? Add in there, what's the cost of downtime? Right? We often look at our operations people and tell them you've got a decision to make, and they say, well, I can't shut it down because I've got product to make. Right? And I realize that product sells for And that's how we make money, is by making product, right? So when we can't make it, what's the cost of that? And when we're down and we're doing reactive maintenance, the time to do that takes longer than it does to do planned and scheduled. Right?
Yep.
So let's build that business case that says, this is what it's worth to do maintenance the right way. We need to start talking business. And that comes right down to our tradespeople. To get people's attention, money is what does it. That's the only thing that changes the behavior, is to point out the money you are wasting.
Alrighty. Adam wants to know if there are any particular software tools that you suggest for RCM, TPM, etc.
Well, I happen to have an RCM tool that's very good. TPM, I'm not aware of one at this point in time. So right now, in the past 3 months, I've been restarting my business, rebuilding a software package for RCM, and my plans are down the road is to say I'm going to have an FMEA tool, I'm going to have a root cause tool, I'm going to have a tool for criticality analysis and so on. So I have those things to work on. Is there one package out there right now that I can think of off the top of my head? No, there's not.
Fair enough. Alexander would like to know, what are the most important measurements to monitor on equipment such as air compressors, and how often?
In terms of air compressors, number one would be your dew point. And I'm a person that says, if you can monitor dew point continuously, do that. So then you would look at differential pressure across your inlet filter, inlet pressure, discharge pressure, differential across your compressor, flow, and again, probably the most important one is dew point. Right. Monitor pressure, temperature, or excuse me, the temperature of the compressor as well, and as well as the coolant that you're using, whether in most cases it's oil. So you'll have your own oil system. Keep an eye on that as well in terms of continuous monitoring. Compressed air systems, by the way, I've done more RCM on compressed air systems than any other asset out there. If they're not maintained properly, the air will have an impact on the reliability of every single one of your assets. Because if you have dirty, wet air, it ruins your instruments.
That was an amazingly thorough answer. Thank you. I'm going to ask you, we're going to keep answering questions, but I'm going to suggest that you advance your slides by one, Doug, so that people can see your contact information, so they can write it down if they want to now instead of waiting. There we go. And then I'm going to go on to the next question by Ahmed. What are some effective predictive maintenance procedures that you can recommend to improve reliability of equipment?
Could you ask that again?
I can. What are some effective predictive maintenance procedures that you recommend to improve reliability of equipment?
Okay, so the top four are, in terms of, and this is confusing for predictive maintenance procedures, so there's really predictive maintenance tools. Right? So we have vibration analysis, thermography, airborne ultrasound, and motor current analysis, and I'll give you lubrication analysis. Those are the five that everybody should be using. You can add an easy one to that, number 6, which is what I call process verification. That's the use of your PLC to monitor and alarm and trend, along with comparative trends, pressure, temperature, flow, amp draw, timing, right? That PLC is there 24 hours a day, 365 days a year, and it gives you information, right? I would encourage you to separate maintenance alarms from operations alarms so that your operators aren't pestered by all those things that come in that we should be having maintenance take a look at. For example, differential pressure, right? And having a maintenance alarm package spit out each morning at 6 a.m. that says, here's the maintenance alarms that came in across our different assets, and assign those to the correct task, whether it's a mechanic, an instrument person, electrician. Go out, take a look at these, see what's going on.
Mm-hmm. All right. And you've got a big fan club here, by the way. People are greatly appreciative of your presentation. Lots of thank yous coming in. So a fellow named Gregory who would like to know whether you agree that the overall category of work in the PF interval is corrective, and how do we classify inspection-only tasks? Do we go with fault finding as an explanation?
In terms of the PF and corrective, that is an accurate assumption. The work that comes out of there is corrective based on we've detected a potential failure, and what do we got to do to correct it to get back to the level of resistance to failure that we would expect. In terms of monitoring and inspection, this is one of those cloudy areas in terms of the field of reliability. Stan Nowlan and Howard Heap called, for example, crack monitoring on aircraft fuselage on condition maintenance. And there's another school of people that says on condition means the equipment is on and running. I'm a person that says, I don't care what you call it, put it in your maintenance plan and do it.
Mm-hmm.
Whether you call it a PM or a PDM task, I'm not one of those people that gets really excited about which category is it in. It's the right thing to do. Go out and do it. Right. Failure finding, and I heard that term used, and I want to make sure that's clarified. Failure finding or fault finding comes into detecting or a task that's performed to detect a piece of equipment or asset that's already failed but not recognizable by the operating crew. So the equipment will run perfectly with an item in a failed state. An e-stop, for example. The equipment will run perfectly with the e-stop failed in a state that if you push it, nothing happens. Right? So failure finding tasks should be put in place to detect those types of things.
Okay. I'm going to move on down to some people that we haven't aired yet, and then I'll circle back around to folks who have submitted additional questions. You have a listener named Anna, who I think because of your earlier success, your great answers, has asked about commissioning baselines for elevator modernization and for air compressors. I think you gave a pretty thorough air compressor answer, but how about elevator modernization?
Elevator modernization. Okay.
Come on.
Yeah, that's a bit outside my field. I've done some RCMs on old elevators, and so to say that I have something that, off the top of my head for new, gosh, there's so much change that's done to them now in terms of how they operate, in terms of using VFDs and those types of things that I can't give a good suggestion with that and have a good heart behind it.
It's pretty specialized.
Yeah.
Bill asks, are there any tools available to help us complete this type of analysis on existing equipment and to determine the remaining useful life of existing equipment? Yeah,
there's lots of tools. RCM is a great tool. FMEA is a great tool. In determining useful life, that's a tough one, right? And I've told people for years, old doesn't mean bad, right? Unless, of course, we're talking about obsolete, right? Because now you're playing with father time, so to speak, right? And making a determination of how long something is going to last. That's possible for wear-based components where we can measure surface loss and things like that. When it comes to electronics, that area becomes really, really gray. And again, there's reliability statistics that would help you with that. Off the top of my head, I'm trying to go back 20 years to my reliability statistics courses. It's saying there's a probability of survival calculation that you can do on random-based components that would give you a pretty good idea, right? Would I gamble my own money on that? No. Right? Because again, you had competing risks of, if we're talking about an electronic component, all right, how many enemies of electricity are present? The calculation doesn't ever think about that. It doesn't think about, is it in a moist area? Is it a corrosive area? Is it in an area where we have electrical outages, so we might see power surges? And that's why I say if it came to putting my own money on it, I wouldn't bet my own money on that calculation. But realistically, those calculations were proven between the airline industry and the aerospace industry, especially NASA did a lot of that through the Rome. They call it the RAC, Reliability Analysis Center in Rome, New York. You might want to search that. There's some pretty good information in a book called The Reliability Tools that came out of the RAC. And I've used that information quite a bit through the years.
Amazing.
If I find my copy, I'll post a picture of it up on LinkedIn today. I'm pretty sure I know where my copy is, so people can look at it, see if that book is still available.
We have time for a couple more questions. I want to remind people that when I close this down, you'll get a survey on screen. And if you use that survey to indicate if you want a copy of the slides, we'll send one to you. So wait for the survey, fill it out. We'll get a copy of the slides to you. And that the full recorded session with all of Doug's magical answers here is going to be up online on excelix.com not too long from now. So if there's parts you want to re-listen to, you'll be able to. I'm going to go right back to questions. We have one from Joseph, and he asks if is there any equipment or assets that you do recommend reactive as a maintenance strategy?
Yeah, as part of RCM, you're going to learn that run to failure is actually a maintenance strategy for a lot of low voltage components. Proximity switches, I/O cards, read switches. There's not much you can do to those. I mean, it's make sure you got them in stock and make sure you use good, robust brackets when you install them, which make them easier to replace and make them last longer.
Joseph also asked whether excess lubrication has any effect in an open system, like a pump where the excess is vented.
Excess lubrication?
Mm-hmm.
Yeah. It can be just as bad as not lubricating it. So,
pretty much.
Generally, I mean, it's just another point to bring contaminants in, right? And you can overpressurize a bearing, for example, by over lubricating it. You blow the seals, then the next thing, once the seals have gone, you've got an entryway for contamination, and you've ruined the life of that bearing.
Mm-hmm. Richard has a question that I'm not sure if it's in your bailiwick or not, but he asks, should you service vehicles before the vehicle computer says it's due? Is that helpful or more wasteful?
On a vehicle?
Yeah.
Yeah. I've had lots of fun conversations with my fellow reliability engineers at conferences about this, and we all vary from one extreme to the other, which some say everything in the manual is a bunch of hooey, to the other that said, yeah, I'm doing my oil strictly 3,000 miles, somebody else at 5,000 miles. Look, it depends on what lubricant you're using, right? And I tell people, I'm almost embarrassed to say this. I think it was just 2 years ago that I went and got my MLT certification, level 1, right? And I learned so much that I didn't know about lubricants. And we, in those classes, discussed the intervals that are recommended by the auto manufacturers, right? And they're typically, it's a CYA interval that says, based on everything we know where people drive cars, hot areas, cold areas, dirty areas, dirt roads, smooth roads, right? If you're in all those worst case things, here's how often you ought to change your oil, right? What nobody's done, right? I have one friend that claimed they did, but we never did see the results. We're still waiting today to say, I actually took analysis of my oil over the life of one vehicle, right? And now I do it based on that particular interval, right? And he was a person that standard weight oil said he was going 4,500 miles. Right, and that's now his new interval. So I'm a person that says, all right, so what do you do in the spring and the fall if you haven't done 4,500 miles? Because now your humidity changes and you're going to get a little bit of water in your oil.
Sounds to me like you need a radio show, Doug. You're doing great here. So it is on the hour. I feel like asking you one more question, but if you need to go, I understand, and we'll close it down. What do you think?
One more question, and we'll close it down.
All right. What is your view of prescriptive maintenance?
My view of prescriptive maintenance is the maintenance strategy that comes out of using a tool like RCM that's prescriptive based on known failure modes, right? So here's my asset. It's made up of these 85 components, and in assessing the failure modes of those components, we had some failure finding tasks, we had some on-condition tasks, we have some PM tasks, and we have some things that we've decided to run to failure. That's prescriptive maintenance.
Boom. Thank you. All right, everyone. I'm going to close the webinar. You should receive this survey, and you are welcome to contact Doug directly. You have his information up on the screen. Thank you very much for joining us. We will, anybody whose question we didn't get to, we will provide answers to you directly. And there will also be a follow-up blog posted on excelix.com with some of the most frequent questions and some of Doug's answers. All right. So thank you, Doug, very, very much. This was fantastic.
You're welcome.
Have a great afternoon, everyone.